ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in with me today. I really am glad you're here. Today what we're going to do is we're going to take a look at the law of definite proportions. And so I've got my definition written out here. The law of definite proportions states that any sample of a pure compound will always, notice I've got that capitalized and underlined, will always have the same ratio of constituent elements. And so, ladies and gentlemen, I'm going to plead with you here. Please don't overcomplicate this. It's not as complicated as it's going to seem right at the beginning. If you just keep a simple-minded approach to it, and just say, oh, that just means that my ratios are going to be constant. That's all that's saying, and that's all it's saying. So, like, if I've got sulfur trioxide, for example, that means I'm always going to have 1 mole of sulfur for every 3 moles of oxygen. That is going to be a constant composition for sulfur trioxide. If I'm looking at something, let's say sodium chloride, that means I'm going to have 1 mole of sodium for every 1 mole of chlorine. If I'm looking at copper 2 sulfate, which is CuSO4, that means I've got 1 mole of copper for every 1 mole of sulfur and 4 moles of oxygen. So a lot of you are sitting here thinking, man, this is molar ratios again. And you're right, it really is, right? Because if they have those constant ratios, they're going to have those constant molar ratios, right? And so what this means, and I want you to write this down, it means compounds will have definite molar ratios. That's where we get our subscripts from, right? That means compounds will have definite molar ratios. In parentheses there, put subscripts to remind yourself. That's what we're talking about here. All right? And then also I want you to think, because we've gotten into stoichiometry at this point, that you understand that our masses and our moles are actually related. So if I've got a definite mole ratio, I've also at the same time got a definite mass ratio, right? And so the mole ratio, those are definite, and then our mass ratio is what we're actually going to call percent composition by mass. And what that means is that since the mole ratios are constant, I'm going to have a definite percentage ratio based on composition by mass. And don't overcomplicate that. That's just percentage. Part over whole times 100% equals my percent composition by mass. Now these mole ratios, what I've referred to earlier, where we have these definite mole ratios, I'm going to go ahead and add something here. I wasn't going to, but I'm definitely, now that I'm in the middle of this, I'm thinking our definite molar ratios, I'm going to go ahead and name those, and I'm going to call those empirical formulas. And what an empirical formula is it's just the simplest ratio. It's just the simplest molar ratio of the constituent elements. All right? Okay, so again, please keep the simplicity here, because I'm about to start doing some math with you, right? This is all talking about definite molar ratios, definite percentage composition by mass, and I don't want you to overthink this, okay? All right, and so the sample that we're going to take a look at here, because again, remember, I can take a look at substances and tell, yes, they're the same thing, because if they're the same thing, they have that definite ratio, right? They have that definite composition. So we're going to take a look at 2 samples here. They're both carbon and oxygen containing samples, and I want to know, are they the same substance? Well, remember, there's 2 ways I can approach this, right? I can convert all of these masses to moles and make a mole ratio out of it and get that empirical formula and double check and say, hey, are they both the same? Do they both have the same subscripts? Or I can also check by that percent composition by mass. Well, the first thing I'm going to do is I'm going to check percent composition by mass. So I'm going to take a look. I've got 8.19 grams of carbon. Now remember, the percent composition by mass was part over whole. So I'm going to look at 8.19 grams of carbon divided by 30.0 grams total times my 100%, right? Again, it's just part over whole. Carbon over my total sample. Well, if you do the math on this, you're going to see it's 27.3%. All right? Now, I'm going to do oxygen, right? 21.8 grams of oxygen divided by 30.0 grams total times 100%. And what that is that's going to give me 72.7% if you actually do the math on with yourself. So, what we should understand is that the law of definite proportion states that if sample 1 is the same substance as sample 2, then my percentage composition by mass should be exactly the same. It should be the same. And so what we can do is we can check our percentages here. And we can say, all right, well, this one's 12.3 grams of carbon. I'm going to divide that out by 45.0 grams times 100%. And what you're going to find out is that's also equal to 27.3%. And so now I'm starting to get the inclination, hey, these are probably the same thing, right? And so I'm just going to double check. I'm going to do oxygen here, even though I don't really need to because it's only 2 compounds in there, or 2 elements. And that's 45.0 grams times 100%. And what, lo and behold, that's going to be 72.7%. And so what I can say is, since both of these have the same percent composition by mass, sample 1 and sample 2 are the same substance. Now, at this point, I don't know what substance they actually are, and so I can actually use those percentages and convert them to moles and then make a mole ratio, or I can use the masses they're actually going to give me. I'm going to do both, all right? And so what I'm going to do here is I'm going to take this carbon, I'm going to divide it by its atomic mass, which is 12.01, and then that's going to give me, and I'm going to go ahead and make, I've got moles here, and then over here I've got a mole ratio. So those are my 2 things. So when I do this, I actually end up with, and this is grams per mole, I'm going to end up with 1.02 moles of carbon. I'm going to do the same thing for oxygen. I'm going to divide it by the atomic mass of oxygen, which is grams per mole there. And I'm going to end up with 2.04 moles of oxygen. Now, at this point, you're kind of looking, you're saying, oh, 1 to 2. I can't do that yet. What I have to do to make this a ratio, and this is important that you get it down, to make your moles into a mole ratio, I have to put them in a fraction and divide them. I have to divide them. I'm going to divide by the smallest. And so make yourself a note, put divide by smallest, all right, to go from moles to my mole ratio. So what I do here is I divide by 1.02, I divide by 1.02, and that gives me a 1 carbon for every 2 oxygen ratio, and we know that that is actually CO2, right? And so now I know sample 1 and sample 2 are actually CO2. Now there is a trick to this, and I want you to go ahead and understand this as well and write it down. If we're given percentages, we can actually assume a 100-gram sample, right? And so if I'm going to assume a 100-gram sample, I can actually come down here and I can use these percentages. So what this becomes, 27.3% of 100 grams is actually 27.3 grams. And 72.7 is actually 72.7 grams. And now I can go through the same process here. It's going to end up the same. That's going to be grams of carbon. So I'm going to divide by 12.01, and then that's going to give me, all right, and so that's going to give me, what is this, 2.27? 2.27, that's moles of carbon. I'm going to do the same thing here because this is oxygen, so divide by the atomic mass, grams per mole, and that would give me 4.54 moles of oxygen. And again, now that I've got moles, again, at this point, I'm stuck trying to do this. I'm trying to go from my moles to my mole ratio, and I divide by the smallest. So divide by 2.27, divide by 2.27, and I end up with 1 carbon for every 2 oxygen. So again, I ended up in the same exact spot. So notice I can start with the percentages, or I can just start with the masses, and to get that formula, to get that molar ratio, all I'm doing is converting to moles, dividing by the smallest to get the mole ratio. Now, lots of stuff in here, ladies and gentlemen. Lots of stuff. So what I'm going to do is I'm going to go ahead and walk you through this. We've got substances, right? Which is our big coup de grace thing. We can do a couple of things. We can do percent composition by mass, and this is that part divided by whole times 100% to get to percent composition. I can also use subscripts over here and use subscripts to get to my simplest molar ratio, to get those subscripts, right? And this is known, remember, this is going to be known as my empirical formula. So the simplest molar ratio, those are my empirical formulas, ladies and gentlemen. And then now this is the important part. I can actually use percent composition to get to that simplest molar ratio, and we just go from amount to moles to, I'm just going to put MR there, but it's mole ratio. All right. Now there is one other thing that we're going to add, and we'll talk about this later, but our simplest molar ratio, not every compound exists in its simplest molar ratio, and we do have something called a molecular formula. And a molecular formula is just a multiple of the empirical formula, and so that's probably what you want to put right there, is just put that it's a multiple of the empirical formula. All right, and we'll talk about that later on. That's not going to be discussed here, okay? All right, so lots of stuff, ladies and gentlemen. Please don't overcomplicate this. All we're doing is saying everything has these constant ratios, whether it's by mass or whether it's by moles. Everything has a constant ratio according to law of definite proportions, okay? All right, if you have questions, get them down. I'll see you in tutorials. Otherwise, I'll see you in class.